Determine the volume of the solid, which is created when the area between the curves y equals e to the x and y equals e minus 1x plus 1, so this is a line, y equals mx plus b, is rotated about the x-axis. So we can see, okay, we've got two curves. We have no bounds. The question is not saying, hey, do it from -1 to 2 or something like that. It's not saying anything like that. So we're going to have to come up with the bounds, and we'll do that with points of intersection. We'll also have to, because there's two curves, we'll have to figure out which is the top function and which is the bottom function. Okay. And then we can use our volume formula. Okay. So it's good to have sort of a plan of I'm going to do this, 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 and this. It makes questions like these a lot more manageable if you have sort of a big picture. I'll do this, and once this is done, I'll be able to do this, and then be able to do this. Okay, so we'll start with the bounds. Now it's a little odd because we got an exponential function and we're going to be equating it to a polynomial. And so you might start looking for the bounds like this and say, okay, here's our curves. Y equals e to the x. And then e minus 1x plus 1. There they are. Now I'm going to draw a quick sketch in just a moment to show you off. But if you're just trying to blindly use algebra, you might get stuck pretty quickly because you set the expressions here equal to one another. And you say, I don't know how to, like, I was never taught how to solve things that have exponentials in them. And, even if you have, it can be a bit of a slog to do. So my recommendation, if you encounter sort of polynomial have to be equal to exponential or exponential have to be equal to trig, almost always the questions are set up with nice values, right? I would not expect the answer to this to be something like x equals 27 root 2 all divided by pi, right? That would just make for a very ugly problem and an ugly integration overall. So you might want to check nice simple values, right? Values that make the curves both sort of happy. So things like x equals 0, okay? X equals 1, x equals minus 1, x equals 2, until we start finding points of intersection. And if you do go through that, x equals 0, you'll get 1 equals 1, so that is 1. And I think x equals 1 is the other one. So you'll get e minus 1 times 1 plus 1. And then so that's, this is e minus 1 plus 1. And look at that, e equals e. So you do get 2 points of intersection by just checking. But the whole point I'm just trying to say is if you have sort of a weird thing, you're like, oh, I don't know how to solve, sometimes just checking some nice values can help you out. That said, maybe you don't want to do this algebraically. I would say this is a lot easier to do graphically, especially for the next step, which is figuring out which function is on top. Okay? So being able to graph quite nicely would make this a dream. Okay? So e to the x is the one curve, and we know exponentials look something like this. Okay? And we've got, 0, 1 is one of the points on there, and 1e, and like 2e squared is up here, and there's other values that we can label. But for the curve here, or sorry, not the other curve here, which is the line, well, we can see right away y equals mx plus b. We've got an intercept here at 0, 1, which is great. And then you go over by 1, up by e minus 1. So over by 1, up by e minus 1. You can pretty quickly get another point on here. And that's also 1e. And you can see, oh, okay, the line just goes just on top. I'm going to draw another version of this, maybe a little more exaggerated. Because depending on your resolution, you cannot see that. So we'll make this super exaggerated. Wah. And the line goes like this, but the line is on top. The line goes directly between these 2 points, whereas e to the x sort of bows sort of bows out just a little bit below. So we don't need the test values if you can see, oh, e to the x is the bottom function, and the line here is the top. So this is e minus 1x plus 1. And you can see it's the top function. And again, our points of intersection are at 0 and at 1. 0 for x, 1 for x. So this gives us the bounds for the integral we're going to set up for our volume. And again, visually, we can see which function's on top or bottom. If you didn't want to do that, you would have to start saying, well, at a half, we're over here, but at a half, this thing is root e. And it could be a little tricky, especially if you don't have a calculator handy. Like calculators make those sorts of things easier, but they don't make the rest of the math noticeably easier. But no, with a quick graph like this is easy. We got the bottom function, we got the top function. So our formula for the volume between these two, so it's 0 to 1, take the bounds, then it's pi, and then bigger function squared minus smaller function squared. So e to the x squared, or e to the 2x here. And then, well, let's not be hasty, we'll just sort of do e minus 1x plus 1. We'll have to expand this square out. Well, that's okay. So we'll have pi, or you could bring the pi out. So we'll have e minus 1 squared x squared plus 2 e minus 1x plus 1, and then minus the e to the 2x. Polynomial part, pretty easy to integrate, and we could do a quick substitution, or here's a really handy trick. If you're trying to integrate e to the anything x, it's e to the anything x over that anything, as long as the anything a is not 0. Okay? The handy little tricks, it helps you avoid substitutions and things like that, but we definitely could do a substitution if we had to. So we got the pi here. E minus 1 squared is a constant. The x goes to x cubed over 3. 2e minus 1 is a constant. The x here graduates to x squared over 2. So those will cancel out. The plus 1 just goes to x. And then we get minus e to the 2x over 2. And we're going to plug in 1 and 0 and take the difference. Okay, so let's get through. So we'll plug in 1. I'll do that in red on the next page. So we've got pi e minus 1 squared, 1 cubed over 3, plus e minus 1 squared, so that's just 1, and then plus 1, minus e to the 2 times 1, so that'll be e squared over 2. Okay. So there we go, and then we'll do the next one in blue, so minus pi, and we'll plug in 0. The nice thing is, all of this stuff's going to go away when we do the 0. So we get 0 plus 0 plus 0 minus e to the 2 times 0. Oops, not over 0, but over 2. Okay. And now we just clean this up. So we'll have pi e minus 1 squared over 3 plus another e minus 1 plus 1 minus e squared over 2. And then all of that minus pi, this is 1/2, so minus, so it's actually plus 1/2 times pi. Bringing the pi's out everywhere, e minus 1 squared. I'm going to start getting a common denominator of 6 for everything. So we'll say 6 and 2 here, 6 e minus 1s over 6 here, 6 over 6 here. Actually, the plus 1 here and the minus 1 will cancel out, so we can really just say this is 6e over 6. Minus e squared, 3e squared over 6, and then plus, so we took out the pi, so we'll say plus 3 over 6. Okay. The next thing I would do, maybe expand out the e minus 1 squared if I want sort of a very nice tight answer. So we've got our pi, we've got 2, we'll say e squared minus 2e plus 1, all over 6, and then it was plus 6e over 6. To go back again, minus 3e squared over 6, and plus 3 over 6. So expanding this out, that's 2e squared minus 4e plus 2. And we can start collecting like terms. Could put everything over 6, really. So we got 2e squareds minus 3 of those e squareds. So we'll say minus e squared at the end here. Minus 4e's plus 6 more of those e's, so that's 2e. And then we had 2 plus 3, so that'd be plus 5. So there we go. There's our final answer. There's a couple ways we could write this volume. Maybe pi 5 plus 2e minus e squared all over 6. All done.